Hello everybody and welcome to the NPTEL online certification course on microelectronics devices circuits. What we will be doing today is basically look into the high frequency modeling of the bipolar junction transistor of the MOS devices. In our previous section we have seen what are the various capacitive components which are there within the MOS device. We also saw that if you have a MOS device and if you have a capacitive model, it can be predicted as a capacitance, for example the overlap capacitance, then it can be written as like this 1 upon j omega c. So, at high frequencies your omega is obviously very large, which therefore your XC's are very low, and therefore at high frequencies I can actually short all my capacitors, right, short capacitors. Whereas at low frequencies just as the name suggests, we will open circuit the capacitance, right. But this is only true for certain range of capacitances, right, which for certain range of frequencies. So, at very high frequencies you need to short it, and certain open frequencies you need to close it. So, what we will be looking today is that if I take a common source amplifier, let us for example MOS based common source amplifier, and we have all those capacitances which is parasitic capacitances as well as bypass capacitances as well as blocking as capacitances, then how does my amplifier behave is the main course of study at this module itself. So, let me come back to the slide itself and show you how it looks like, overall a system looks like. So, to your left, if you look at this point, this is basically your CS based common source based design of a common source amplifier, and I have attached current source onto the source end, and there is a CS which is the emitter sort of a source bypass capacitance. You also have a coupling capacitance CC2 here, which couples the drain output to the output of the drain of the MOS device to the output V0, and you also have a CC1 which is basically the input coupling capacitances, which connects your V signal input signal to the gate of my MOS device, right. RG is the gate capacitance resistance, RG is the drain resistance, and of course there will be also an RS, but since it is in series with a current source, RS will be negligibly small as compared to an output impedance of the current source, and therefore that RS is missing at this stage, and RL is the load resistance which you see here. Now, if you plot on the y axis V0, which is the output voltage, divided by V sig is basically the signal input voltage, and if you make it in dB, so 20 log of V out by V sig, if you try to find out, this will give you in dB, right, and then you try to plot it with frequency on the x axis, right, and this is basically in log scale. Typically this is in log scale. So, you will have 1 hertz, 10 hertz, 100 hertz, 10 to the power 3, 10 to the power 4, 10 to the power 5, 6, 7, 8, so on and so forth. So, this is, so you please understand your y axis will not be a linear scale, it will be basically a log scale, right, and your x axis will be a component sort of a transfer function which gives you output voltage by input voltage expressed in dB and mod of that basically. So, V0 by V sig mod of that in dB. Why mod of that? Because at this stage we are not interested whether you have a phase difference or not. So, we are just interested in looking at the magnitude component available to you. Now, if you look very carefully in this slide or in this overall approach, you will see that typically somewhere between FL, which you see here, we will discuss this later on, and FH, your gain is almost constant. See, so you are plotting a gain versus frequency, and this gain is almost constant, right, it is independent of frequency, it is independent of anything else, right. This band is known as mid band. So, mid band frequency, right. So, what is the mid band frequency? Mid band frequency is that frequency across which the output or the gain is independent of the frequency which you see, right. Now, beyond that particular point, beyond this FH and beyond FL, as you go on increasing frequency or decreasing frequency, your gain starts to fall down, right. This is what is happening, right. So, what we see therefore is, if you properly plot it, is that you get a very steep profile here, you get a very steep profile here, but somewhere in the middle you will have automatically a gain which is almost independent of frequency. This is known as mid band, as I discussed with you. This is mid band, this is low frequency band, and this is high frequency band, right. And a time might come that at such a large frequency your gain will be absolutely equals to 0. So, let us see why this happens, or why you actually see a drop in the gain at very low frequencies and at very high frequencies. If you remember, if you look very closely and if you remember your previous discussions, you will appreciate that you will always have a coupling capacitor here and a coupling capacitor here, and you have a CS which is basically a source capacitance. Now, why these capacitances were used initially? They were used primarily so that, for example, why CC1 was used? CC1 was used primarily so that any DC component of this V sig. So, V sig is basically an AC signal. So, it is basically A sin omega t, but since it is derived from a DC, you do have a source available within itself, there will be a DC component always associated with V sig, right. You do not want that DC component to sit on the gate side of this MOS device, otherwise it will change the bias point, and that is the reason you put a CC1 here, a coupling capacitor, in fact known as a blocking capacitor. And as a result you only allow the AC signals to go through and you block the DC. Similarly, if you look at CC2, this also allows only the AC signals to go through and block the DC, right. So, you only allow the AC signals to flow through and block the DC. Which DC? DC coming for example from VDD, right, coming from VDD, this will be blocked by CC2. So, that is the reason, but then let us see what happens therefore at low frequencies. Now, at low frequencies, as I discussed with you, Xc was equals to 1 upon j omega c, which primarily means that at low values of omega, Xc will be typically large, right. So, as well as this, right, its effective value is typically very large, the resistance offered by this is very large, and therefore as you start to lower your frequencies, they start to behave more like an open circuit rather than short circuiting, and therefore your gain starts to fall down, the gain, so your gain drops, right, your gain drops. Why does your gain drops? The gain drops because of the simple reason that as you lower your frequency, 1 by j omega c goes on increasing, Xc goes on increasing, and then the assumption that you are shorting it, now you have to open it to a larger extent, and as you make it open, obviously you can understand there will be no signal flowing and therefore your output will be equals to 0. That is primarily the reason why the gain falls at the low frequency band, right. Let us look at the fact what happens in the high frequency band, which is somewhere here, more than FH, right. If you look at more than FH part, then remember there were two components, parasitic component known as CGD and CGS, CGD and CGS, gate to source and gate to drain capacitances, right. Now, at such high frequencies, at these what we were assuming was that these capacitances were not playing a role because the overlap is small or they are minuscule, they are very small in dimensions, but at such high frequencies of operation, right, the resistance offered by CGD and CGS though is relatively small, but the gate to drain capacitance which is available to me has a extra effect onto the circuitry and gain starts to fall down, which means that at such a high frequency, though Xc is low for CGD and CGS, right, which means that your gate and drain are not coupling properly in a sense, and therefore gain starts to, so gate starts to lose control over the channel in a sense, and as a result the gain starts to fall. So, the high frequency, the gain reduction is primarily by virtue of reduction in CGD and CGS, right, and your gain losing control over the channel and on the source and drain side, and on the low frequency part, if you look very carefully, it is primarily because of the CC1, CC2 getting effectively shorted, sorry effectively open, and then when they become open the gain starts to fall down, right. So, this is the two reasons why primarily you see this. So, most of the characteristics on amplifier circuits will look like this. This is 20 log AM, AM is nothing but this is AM, this is AM, right. 20 log of V0 by V sig in dB is defined as this point, right. Now, let me come to two important cross points in this characteristics, and these cross points are this one and this one, right. So what you try to do is you just look at the top, suppose this is equals to say a 60 dB, then what you do is you try to go from here to 57 dB. So draw a wire which is 57 dB, so 3 dB drop is there, and then check out 2 points where you get the 3 dB drop. Then we drop the point across the frequency axis and we define FL as the lower cut of frequency and FH to be equals to higher cutoff frequency, right. So, I have a lower cutoff frequency and I also have a higher cutoff frequency. The lower cutoff frequency is the point where the gain has dropped by 3 dB, and higher cutoff is also a gain point where it has dropped 3 dB. Now, therefore, the distance between the two in frequency domain is defined as my bandwidth, right, also referred to as a 3 dB bandwidth. So, bandwidth is defined as difference between higher cutoff to lower cutoff, right, and this is known as bandwidth. If FH is obviously much larger than FL, so FH is 10 to the power 7, 10 to the power 8 and FL may be hardly on the order of 10. So, if we subtract the two, it is approximately equals to FH. So, whatever will be the value of FH, that will be the bandwidth of the input signal, right. Now, if you look at the mid frequency gain, right, mid frequency gain which is basically your AM, then it is V0 by V signal, and V0 by V signal, how did I find out, or how did I come to know was that if you look at so if you go back to your previous slide, sorry, let me just drop this point for clarity's sake, right, and let us look from this point of view, right. If you look this point, Vsig actually is the Vc is the voltage given by the signal, but some portion of that goes at R6, Cc1 and so on and so forth. The remaining falls across Rg, and that is the gate voltage given to this MOS device, right. So, if you look at the next slide here, you see Rg by Rg plus Rsig is the division which you do, because it is basically a voltage divider network. So, it is Rg, so this is Rg divided by Rg plus Rsig is the voltage divider network which you see, this one, right, multiplied by, because this is the voltage divider network, multiplied by Gm into Gm parallel RDRL, right. Why? So, it should be actually 1 by Gm RDRL, right. So, it is basically Gm transconductance. So, if you remember, gain was Gm times Rd, remember. So, this is Gm and this is your effective Rd which you see, but this factor comes from the fact that not all the signal voltage appears across the gate side, a part of it appears because of the potential divider technique. Because of potential divider technique, so if you are giving V6 say is equals to 2 volts, not all the 2 volt will appear at the gate side, maybe 1.5 peak to peak will appear. What is the reason for that? The reason for that is that you do not want large signal distortions to play into picture. So, if your input is very large peak to peak, then you might end up having a nonlinear distortion in your system, right, and as a result what will happen is that your output will be heavily distorted as compared to your input, and as a result you will never get a linear profile which is there with you. So, I discussed with you just now that a bandwidth is defined as FH minus FL. Since FH is many orders larger than FL, we define that bandwidth can also be written as FH, just the value of FH itself. A very important figure of merit which we typically use in amplifier design is defined as the gain bandwidth product. We also refer to as gain bandwidth GB, and it is referred to as AM multiplied by bandwidth, and this is generally constant. So, what you do is that if you want to therefore make your bandwidth high, you have to reduce your gain, so that the product of these two remains constant, right, and that is the problem for any amplifier, that if I want my gain to be high, my bandwidth will be restricted, and if I want my bandwidth to be high, my gain will be restricted. You cannot take both of them together and make both of them high, right, and that is the sort of a price you pay for designing this basic this problem area, right. With this knowledge, let me do a mathematical treatment for high signal frequency and low frequency response. So, if you look here clearly for the high frequency component, if you remember in the previous I have just replaced the MOS device with its equivalent circuit model pi. So, this is basically your pi model of BJT is used, right, of BJT is used. And if you look carefully, it is CGD here and you have got CGS here, you have got current source GMVGS and R0 RD RL, right. So, if you look from this side, from the left hand side, which is the input side, then a part of Vsig appears on the gate side given by this formula. So, Vsig into Rg upon Rg plus Rsig is the effective value. Then what we do, Rsig prime equals to Rsig, because these two will be in parallel. So, Rsig prime will be equals to Rsig parallel to Rg, and then the same voltage is fed into the gate side, which is internally having a CGS, gate to source voltage, which is available with us, and this is the input side. So, fine. And therefore, what people have found out over the years is that Rsig prime, right, Rsig prime will be approximately equals to Rsig parallel to Rg. But since Rg is much larger as compared to Rsig, what we safely can write down is Rsig prime is approximately equals to Rsig, which means that if you go back to your previous this slide, then Rsig prime, which is the potential or the resistance offered to the gate side, is exactly almost as the offered by this structure, right, and that is what we get from here in this case, right. Okay. So, this is what we get. So, if you look at the pi model, therefore looking from this side, what you can do, it's quite an interesting summation, that so when you are doing a high frequency modeling, or when you are doing a low frequency modeling, CGD will come into picture, CGS will come into picture, and therefore they will change the output characteristics of the device, right. Now, if you look very carefully, then what happens is, this is the input voltage which you see. In the output side, quite interestingly, I get CGD multiplied by 1 plus GM RL prime, right. I am not deriving it in the class, but CGD or C equivalent or input capacitance will be CGD into 1 plus GM RL, which means that initially the device would be looking only at CGD, but because of a coupling between gate and drain, right, you have a multiplication term 1 plus GM times RL prime. This phenomena is known as Miller effect. This is known as Miller effect, right, and therefore I get the overall voltage will be GMRD. So, GMRD is nothing but GM times RL into VGS. Why? Because GM is del ID del VGS. So, this VGS cancels with this VGS, ID into RL will give you the output voltage V0, right, and from here you can get the value of output voltage in a much easier manner, right. If we now therefore come to the low frequency domain of this device, maybe we can explain to you. So, right. So, let me come to the So, if you see very closely, or if you have a look at the we also do the low frequency modeling, then in the low frequency, as I discussed with you, right, all the capacitances will remain because they will not be closed as such, and therefore I can write down something like this as the overall gate to source variation, right. So, this is RD, RG, CC1, Rsig, and this is Vsig. This is grounded, right, and then this is also grounded because DC biases are missing, and you have CC2, right, and then you have got RD or RL as part of it. This is CS, right, and this is your plus minus VG which you get. So, looking from the source side, the impedance offered is 1 by GM, right. So, keep this in mind as standard methodology. So, I can write down VG to be equals to Vsig, right, into Rg plus Rg plus 1 by SC C, we get SC plus Rsig, right, and therefore I can safely write down Vg to be equals to a Vsig into Rg divided by Rg plus Rsig multiplied by S upon S plus 1 by CC1 Rg plus Rsig, where this value is referred to as omega p1, or the first point cross point frequency, first cross point frequency is Rg plus R sig 2, which means that the first cross point frequency or the frequency beyond which you will see a drop in the gain is governed by the CC1, the coupling capacitor attached here, as well as the resistance offered by the Rg and Rsig value. Now therefore ID as I discussed with you is Vg times Gm will be Vg upon 1 by Gm plus 1 by SCS, fine. Why? Because looking from this side, if you look very carefully, 1 by Gm is the source impedance as well as 1 by SCS is the impedance offered by this capacitance. So since they are in sort of a parallel connection, therefore what you do is that you add them up, and therefore Vg upon that will give you the value of drain current, right. So if you solve it and if you want to get the picture, I get Gm times Vg S upon S plus Gm by Cs. This is your ID, right, and therefore I get a second crossover point omega p2 as Gm by. So I have a first crossover point given by this and the second crossover point given by this, right. You also get I am not deriving it in the class, but you also get a third crossover point which is given as omega p3 is 1 by Cc2 into 1 by Rd plus Rl, which means that each of the capacitors Cc1, Cc2 as well as Cs, right, starts to give you extra dip in the output characteristics. So as you lower your frequency domain, they start to fall drastically. So if you plot its frequency, if you plot its frequency versus gain graph, then you get something like you have a 3 dB bandwidth obviously available with you. This shows a drop here, and then this shows a drop here, and then this shows a drop here. So if you look very carefully, this is your FH, right, this is your FL, FH, and this is your FP3 and this is your FP1. This gives you approximately 60 dB per decade drop, this gives you 40 dB per decade drop, right, and then FL is there, which is the low frequency gain which you see, right. This is nothing but 20 log of AM, right, where AM is the gain which you see, AM is therefore equals to V0 by V sig for a fixed value of this value, right. So this is what you get from the gain, and therefore if you look carefully, then we get what you get is basically Cin is equal to Cgs, right, plus Cgd into 1 plus Gm times RL, right. So let me do this is for the low frequency design, and therefore let me do for a high frequency design to make to make it much more better understood, in the sense that we can make it high frequency design. Within the high frequency design, we also try to find out or try to see what is known as Miller multiplication. So I have got two ports here, 1 and 2, and let us suppose input voltage is V1 and output voltage is kV1, which means that the input and output are related through a constant multiplication factor k. Then this, and this is Z is the impedance, then this is equivalent to saying as this Z1, right, and then this is Z2, right, and Z1 is referred to as Z upon 1 minus k and Z2 is referred to as Z upon 1 minus 1 by k, right. I am not deriving it in the class in this lecture, but this is how it looks like, and and this is known as this is known as Miller effect. So Miller effect tries to enhance the overall gain by making coupling between gate and drain in a much prettier fashion or easy fashion, right, and that is what we get from the Miller capacitance as such. So with this what we have done therefore is that we have actually seen therefore that, as I discussed with you, for every one pole added to the right you get, so for an nth order filter for example, this is known as the decade or the roll off rate is always given as 2 to the 2n dB per decade, which means that if a second order system is there, right, then it will be 40 dB per decade because n is equal to 2. If n equals to 1, then a single order will have 20 dB per decade, fine, and you can see therefore that this is how it forms. So you backtrack this one on the back side and you backtrack this one. The cut is basically your half your FH, which is the basically your high band design. As I discussed with you earlier, therefore V0 by V6 will be given as AM upon 1 plus S by omega h, and omega h is given by this formula, FH equals to 1 by 2 pi C in into R sig, right. R sig is the approach value of voltage, where C in is written as CGD plus CGD into 1 plus GM into RL. So as you can see that adding an extra potential or a capacitance in the feedback loop in sort of in a loop, and assuming that CGS will always come into picture irrespective of any other thing, we see that my input capacitance can be raised from a value CGS to CGS plus this whole quantity, and that is quite an interesting and impressive one, that by doing so you will be able to raise the overall gain of the system, right. Let me come to the high frequency model of the CS. So that was the low frequency model, and let me come to the high frequency model as I discussed with you. If you look very carefully, this is again the same thing, Rn equals to Rg, and from looking from this side it is only Gm, right, it is only Gm plus Rs. So the resistance offered at the source end is 1 by Gm plus Rs, right, and then if you divide Vi input voltage by this quantity is basically the current which is flowing through this resistor R, right, and that is what the current is. Now since the current has to be the same, I see that Vi into this quantity and this quantity will also be remaining the same. So on the right hand side R0 will be equals to Rd, which is basically the input impedance which you see from here. Now if you replace this MOS device by its corresponding T model, then we say that I will be equals to Vi upon 1 by Gm plus Rs, 1 by Gm plus Rs, total current flowing. Since on the gate side, from the gate side you do not have any exiting or entry of current, almost the same current will flow through the resistor, and the evidence is that there will be a 1 by Gm drop there, and therefore looking from the source end it is Vi upon 1 plus Gm plus Rs, right. So looking from the source side, current and both the currents are equal, and therefore there is no problem in as far as understanding the configuration is concerned. So we have finished with high frequency model and we have seen how frequency model works. Let me therefore recapitulate the whole discussion on this topic. The figure of merit for high frequency operation of MOSFET as an amplifier is the unity gain frequency. How do you define unity gain frequency? Where the gain falls to 1, we define that to be as the unity gain frequency. Ft or the transit frequency is proportional to Gm and inversely proportional to the FET internal capacitances, which means that higher the value of Gm, more will be the bandwidth and more will be the your Ft. But if your internal capacitance is also high, then your reduction will be there in your Ft as well as Gm. The higher value of Ft, the more effective the FET becomes as an amplifier, right. So one thing which we learn is that your Gm should be high and your Ft should also be high. Once you ensure these two to be very high, then automatically everything falls into place in a detailed manner. Miller effect occurs due to gate to drain capacitances, right, and this is quite an interesting problem which people face, that the Miller effect, which we will do maybe the next turn and I will show it to you how Miller effect works out. But Miller effect does what primarily is that it adds to the overall capacitance of a system, and that addition is also not linear, it is effective addition. So there is some constant, you multiply that with CGD to get the new value of CGD. So gate to drain coupling capacitance is there. Now Miller effect therefore works due to gate to drain capacitances, that is what we have just now understood. The most useful band of amplifier is basically your mid gap band. Why? Because the gain is almost constant and independent of the frequency, and therefore I can safely say if you are operating your amplifier within that range, my output will be almost constant depending only on the value of AV0, right. Then we have two important frequencies we have seen, FH, which is also referred to as low cutoff frequency, high cutoff frequency, and FL, which is basically referred to as a low cutoff frequency. They are typically 3 dB points below the maximum gain position, and beyond these points the gain starts to fall down with increasing or decreasing frequencies, right. So the most reliable one is basically your the mid band frequency. Last thing is that there is a merit, figure of merit, which is basically known as gain into bandwidth, which is also known as a gain bandwidth product. That should be always constant for a system. So, if you are increasing the gain, pay the price of a lower bandwidth. If you are increasing the bandwidth, you pay the price of a lower gain, right. So, with this we have almost learned most part of the amplifier design and look into the very critical aspect of amplifier design. Next time we will take up another issue as far as this course is concerned. Okay. Thank you very much for your patient hearing.